The supermassive black hole at the center of our galaxy, the Milky Way, is flickering. And we know that thanks to observations taken in the past few years with the James Webb Space Telescope, JWST, which were published this month by Yousafzadeh and collaborators. Now, just to be clear here, what's been detected is not light from the black hole itself, because famously, black holes are so dense and their gravity so strong that not even light can escape them. What's been detected is light from the region around the black hole, what's known as the accretion disk, a swirling, glowing maelstrom of material orbiting the black hole, which will eventually fall beyond the event horizon and add to the black hole's mass. That material is accelerated to huge speeds so that it gets hot and it glows so that we can see it. And it's by studying that glowing material that we can work out what's going on in this turbulent region around black holes and study how black holes are growing. Is it a smooth growth, or is there a lot of turbulence which causes the light we receive to vary and flicker, which is what's been seen by JWST for our supermassive black hole, what's known as Sagittarius A star. So in this video, we're going to dive into this new study by Yousafzadeh and collaborators, and we're going to chat first about how the light from around black holes is actually generated, second, what's actually been observed with the James Webb Space Telescope, and third, what this means for how the Milky Way's central supermassive black hole is growing. And if you find yourself wanting to brush up on your knowledge of black holes after watching this video, then you've got to start with the basics, which is where Brilliant, the sponsor of this week's video, comes in. Brilliant helps you get smarter every day with thousands of interactive lessons in maths, science, programming, data analysis, AI, and more. Learning a little bit every day is one of the most important things you can do for your growth, like personally and professionally. And if you're anything like me, you'll constantly catch yourself just mindlessly scrolling online, which, let's face it, is just a waste of time. It's not productive. Thankfully, Brilliant is the exact opposite of mindless scrolling. It's actively helping you get smarter with just a few minutes a day. And if you're here on my channel, then I know that you must be interested in learning more about science. Brilliant science courses help you make sense of our universe at every level, from the mechanics of simple machines all the way up to the mind-bending physics of black holes. With Brilliant, you can develop your scientific intuition through visual, interactive problem solving that gets you hands-on with key concepts. So to try everything that Brilliant has to offer for free for 30 days, head to brilliant.org/Dr. Becky, or you can click on that link in the description down below, or you can scan the QR code up here, and you'll get 20% off an annual premium subscription. So a big thanks to Brilliant for supporting this channel, and now let's dive in and chat first about how this light around black holes is generated. Because as I said, despite black holes themselves famously not giving out any light, the regions around black holes are actually some of the brightest objects in the entire universe, and there's actually loads of different sources of light that you can get from those regions. Let's start first with the accretion disk itself, which is material like hydrogen gas that's accelerated to huge speeds due to the black hole's gravity. Traveling at such huge speeds means there's a lot of friction between the particles as they move around the accretion disk. That buildup of friction means a buildup of heat. The buildup of heat means they start to glow with what's known as thermal emission. That's true for any material in the universe, not just for the material around black holes. And essentially, the hotter the material, the higher energy light that you're going to get given off. Black hole is a very high energy environment, so unsurprisingly, you get a lot of high energy light given off, usually for black holes in the form of X-ray light. So very energetic, short wavelength light. And that is how we see a lot of black holes with X-ray telescopes and know that they're there and that they're growing. Whether that's black holes the same masses of stars in our own galaxy, or supermassive black holes found at the centers of distant galaxies. Now that X-ray light that's given off then has a massive sort of like knock-on effect on all the stuff around the black hole as well. So for example, the X-ray light might hit into a hydrogen atom, and that could cause that hydrogen atom to glow with a very specific color or wavelength of visible light that we can see with our eyes. And when we take that light and get a trace of how much light at each wavelength we see, we get a nice big peak, and we know that there is a black hole there that is growing. Or that X-ray light can actually impact with dust surrounding the accretion disk, which is usually found in like a donut shape, what's known as a torus. Dust being like, heavier, bigger molecules that block that higher energy light, so that short wavelength light, like X-rays. The dust actually absorbs it and then re-emits it at infrared wavelengths of light that we can then detect with infrared telescopes. Then there's also something known as synchrotron radiation. This is when electrons, so like negatively charged particles, kinds that you find like whirring around the nucleuses of atoms, when electrons are moving in magnetic fields and they also start to glow and give off light. Specifically, this happens when an electron is being accelerated in a direction perpendicular to the direction it's moving in, perpendicular meaning at 90 degrees. So you've got an electron orbiting a black hole that's always pulling in because of gravity, being accelerated, you know, like perpendicular to the direction it's moving in because it's towards the black hole as it moves around the black hole, then you're going to get some synchrotron radiation. And again, the electrons give off light over a huge range of energies, from X-rays all the way down to the infrared. Now, there are many, many other ways that you can get light from around a black hole. I've only covered a few here, but essentially what happens is all of these different ways that, you know, you're emitting light around the black hole have a very distinctive like spread of energies of light that they give off, like a distribution. And all of these different ways of producing light will add together in those distribution of energies, of wavelengths, to give us like an overall distribution of light that we then observe with our telescopes. And so what we're always trying to do is kind of like from the overall that we've observed, piece out what different processes are actually going on around a black hole. But it's not a constant smooth amount of light that we'll get because the accretion disk is so turbulent. It has denser patches and places where material will collide together, meaning the amount of light that we get tends to vary. Of course, the other issue is that when we do observe this, we're using a telescope that's been designed and optimized to work in a very sort of specific wavelength range. You're not going to see the entire wavelength range from like X-rays to infrared with one telescope, sadly. So when we observe, you know, the regions around a black hole with JWST, for example, we're only seeing the infrared light, which is going to be dominated by the synchrotron emission, those electrons moving the magnetic field. And then if there's any of that dusty torus, the re-radiated light from the torus as well. Which brings me to what's been observed with JWST for Sagittarius A star, a supermassive black hole at the center of the Milky Way. So Yusuf Zada and collaborators applied to use JWST to observe Sag A star at two different infrared wavelength ranges of light, centered on 2.1 micrometer wavelength and 4.8 micrometer wavelength. Now, first of all, this is not an easy thing to do because when you look towards the center of the galaxy, first of all, there's a load of stars towards the center of the galaxy, but there's also a load of dust as well. And so you've got a load of sources of light here that you don't care about, right? First of all, you have to mask out all of the starlight, but then also account for that diffuse glow of dust emission in the background to actually isolate like the light from the actual accretion disk around Sagittarius A star that you actually care about, which is incredibly, incredibly small on the sky. And I showed this video before of like the data visualization that NASA released as part of the press release, you know, making it look pretty, but here actually is that data as it was plotted in the research paper. You can see that it's taken across a couple of different isolated days in 2023 and 2024. So you've not got like a constant time axis on the x-axis here. What you see with all the dashed vertical lines actually show where the breaks are in time. So don't read this from left to right as if it is continuous. Then you've got two different things plotted here. In the blue points, you've got the shorter wavelength infrared light, so things at higher energies. And then in red, the longer wavelength infrared light at a lower energy. The black and grey points then show two different reference stars from elsewhere in the image, which are fairly constant in their light output. And that's really important that they show that as well, that the reference stars don't really change in brightness, while you do see Sagittarius A star like varying in brightness, because it shows you that like those variations are not like noise in the image, not something that's like systematic across the whole image that's to do with how you've done your data processing. Like you're getting static light from the stars, and any variation you see, you know, is like a true physical variation of the accretion disk around the black hole. And so what you can see is that the Milky Way's supermassive black hole accretion disk is always varying in brightness, right? You've got the low level variation that's happening all the time, and then a few isolated, much brighter flares. Now, it's not just the brightness of the light that you can look at. There's a couple of other things that you can pull out of this data as well that give you clues as to what's going on around the Milky Way supermassive black hole. The first is whether there is a time delay between the two different wavelengths, the two different energies of light that have been studied here. So for example, if you match up the peaks of the fluctuations that you see in the 2.1 and 4.8 micrometers wavelengths of light that have been studied in each of the days observed, Yusuf Zadeh and collaborators find that there was actually a range of time delays between the two, from about a 3 to a 40-second difference in the time that the light arrived, with the higher energy light, the 2.1 micrometers, arriving first, and then the lower energy light, that 4.8 micrometer wavelength, arriving just a little bit later. Second thing you can look at is what's known as the spectral energy index, which is essentially like the steepness of that rise of how much light at each wavelength you're getting, right? It peaks at some energy or wavelength of light, but it'll rise up really steeply and then gradually fall off. You can look at the steepness of the rise or the steepness of the descent. And that actually tells you a lot about, the process that's giving out that light. So here you're going to be dominated by that synchrotron emission, right? The electrons moving through the magnetic field. And so the steepness of either side is going to tell you things about the process that's giving out that light. So like the density of the electrons and how fast they're moving, but then also like the strength of the magnetic field that's producing that emission as well. Now here, they've only observed two different wavelengths, so they don't have that full distribution of energies of light that have been received, but there's two different ones, right? So you could say, is there more light detected at one wavelength or one at the other, and how much more light, and therefore how steep is that rise or that descent in this case. And so Yusuf Zadeh and collaborators do this, and they get an estimate of that steepness of all times in the observations just by comparing the light at 2.1 and 4.8 microns. And what they find is that that low level variation that you see has quite a steep index, so a bigger difference in the amount of light that was seen at the two different wavelengths, whereas those bigger sharp peaks have more of a gradual index, so less of a difference in the amount of light that's being given off in those two separate wavelengths. So with all of those results, that brings us to what does this actually mean for how the Milky Way supermassive black hole is growing? How can we explain those like two different modes of variation, the low level and the flares, and then also the difference in the spectral index you get for those different variations, and then also the time delay between the two different energies of light? So let's start first with those two different types of variability, because Yusuf Zadeh and collaborators think there's two different processes at work here to give that like low level variation versus the big spikes. So for the low level variation, like Yusuf Zadeh and collaborators think that this could just be like random fluctuations in the accretion disk, right? You randomly end up with a denser, hotter spot that will be a little bit brighter for a time before it disperses and the disk averages out again, because that hot spot was hotter, and hotter things glow at higher energies. You will end up with more of the higher energy light than the lower energy light, more of the 2.1 micron to the 4.8 micron, explaining why you get sort of like a steeper index for the lower level variability. Whereas the big brighter flares, Yusuf Zadeh and collaborators think those are caused when two magnetic field lines around the black hole collide and what we call reconnect, which will funnel a load of particles that way, give out a big burst of energy across a whole range of wavelengths, and then explaining why there's not actually that much difference between the amount of light detected at 2.1 and 4.8 microns for those bigger flares, why there's not as steep of an index. You can think of these processes that are going on in this accretion disk to cause this flaring as like akin to what's going on in the sun, right? You've got these low level random fluctuations in the plasma, and then occasionally you get these bigger releases from the sun because of magnetic fields in what we call solar flares. But what about that time delay between the two energies or the two wavelengths of light that was studied? Well, that again comes back to the idea of a magnetic field. And I think it's worth stating here that we do know that Sagittarius A star has a very strong organized magnetic field around it, in part thanks to the Event Horizon Telescope's observations. And so while we don't really understand this fully, Yusuf Zadeh and collaborators' best guess of what's going on here is that the magnetic field is actually causing the particles that are giving out this light to lose energy during the flare, with the higher energy wavelength light actually losing energy quicker than the lower energy wavelength light. But like with any scientific study, we've now got more scientific questions we can ask. Like, are we actually seeing the finest of the variations here? Because we could be losing some in the noise of the image, and so ideally we should observe for longer. And are any of these like smaller variations or even the brighter flare variations, like, are they repeating or are they completely random? And again, to work that out, you kind of got to observe this for longer. So Yusuf Zada and collaborators have actually applied to use JWST again to observe like a full 24-hour period, just to help drill down all the noise in the images that you end up with from JWST, and hopefully then work out if the Milky Way's supermassive black hole is growing with a set routine, or is it all just completely random. I forgot what I was gonna say. Oh yeah, there we go. Put the video back. Blah. Is there a time delay? Time delay is the simpler option there to go with in terms of words. In fact, it's the accurate option to go with in terms of words. Time delay. Delay. It's a simple word, Becky. Now there's two. Oh, there's a bird. Hi. Oh, there's a big bird. Sorry. I will get this. I don't know why I'm so distracted all of a sudden.